So this week we were dealing with conformations of simple organic molecules, and I would like to take a few moments to simply review what we learned in class. So on the screen you see that I have a molecule of N-butane, and we want to look down the C2-C3 bond axis. So if you follow the cursor, I'm going to number this from right to left. 1, 2, 3, 4. And I want to rotate this molecule so that I can look down the C2-C3 bond axis. A couple of things worth noting is that this is the lowest energy conformation of N-butane because the biggest, bulkiest group on the front carbon on C2 is anti. That means it has a dihedral angle of 180 degrees relative to the biggest and bulkiest group on the back carbon, which is C3. And I can rotate this back into the plane to indeed show that the CH3 that was rendered to the right is attached to C2, and the methyl group that was attached to the back carbon once I had rotated it into the Newman projection is indeed C4. So once again, by rotating and looking down the bond axis of the C2-C3 bond, I get the Newman projection of the lowest energy conformation for N-butane. Now, of course, we want to couple this with being practical. I have a new molecular drawing program called ChemDoodle. You can obtain a 30-day free trial of this if you like. It's got a few really neat features, one of which I'm going to show you right now. So I can highlight this molecule and then rotate it in 3 dimensions with a representation that I've rendered in 2 dimensions. So again, C1, C2, C3, and C4. I'm going to rotate, and again you will notice that when I'm looking down the axis of the bond, here is my C1, here is my C4. They are anti one to another, which means that the largest, bulkiest group on the back carbon is 180 degrees or anti from the largest, bulkiest group of the front carbon. That's an arbitrary choice that we make, but it allows us always to use the following generalization. The 180-degree dihedral is always going to be the lowest energy conformation, and while the 0 degrees is always going to be the highest energy conformation. And of course, I can re-highlight this and rotate it back so that I get what I had in the beginning. Now the question is, how are we going to draw the Newman projection for this rendering on an exam question, on a board, on a piece of paper as you're practicing this at home, or on a quiz? So in order to do this, I'm going to draw this on my canvas on the screen as you're watching this movie so that you can try and practice this as well. So first of all, I want to draw the molecule in 2 dimensions. So here is my 2-dimensional rendering of N-butane. And in order to be consistent with what I taught you in class this week, I am going to make a dash and a wedge in the same way that we did this earlier. And I'm only going to draw them on one carbon just to emphasize what happens. Now, as I number the carbons, this time I'm actually going to number from left to right. So C1, C2, C3, and C4. Remember, the front carbon is going to be simply a dot on the Newman projection, while the back carbon is a circle. And as promised, I've been practicing my circles like a good boy. So on the front carbon, on carbon 2, which is our orange dot, I want to render these in orange. And we will have a methyl group going straight up, and hydrogens that go to the right and to the left. So I want to be careful to label these. Again, I am trying to be about as neat as I can be. I really can't do this too quickly because, quite honestly, the stylus is a little difficult to control at this point. And of course, on carbon 3, I'm going to render those in blue. I want the lowest energy conformation, so I want to make sure that my methyl groups are anti, because they are the largest, bulkiest functional groups that I have relative to the hydrogens. This, of course, means that my hydrogens, when I look at a red, excuse me, not a red, but a blue hydrogen relative to an orange hydrogen, they're going to be gauche, or 60-degree dihedral, relative to the orange. So if I start looking at the dihedral between the orange hydrogen and the blue hydrogen, this is a dihedral of 60 degrees. Now, relative to the two big bulky groups, which I'm going to circle in red, my dihedral angle is 180 degrees, and this is the relevant angle that we want to use when we are describing the dihedral for each of these Newman projections. This is one of 6 Newman projections that we actually want to draw for this particular structure. So what we want to do is, as I suggested in class last week, let's hold the back carbon steady, and we will rotate the front carbon counterclockwise in increments of 60 degrees. So what I'm going to do is draw the back carbon 5 times. And each time I'm going to have the same nuclear positions that I drew for the anti-conformation that you already see on the screen. So in each case, these hydrogens and the methyl group will be the same. I will not change them. Unless, of course, I can't draw a straight line, and then I'll erase it so I can do it again. So if you'll bear with me just for a couple of moments, I'm simply going to repeat what I have already drawn. And as I'm going through and doing this, I would strongly recommend that you do the same thing. And then when we get to a problem on an exam, a take-home exam, an in-class quiz, an in-class problem set, this procedure is really nice to follow because it allows us to be consistent and efficient so that we don't spend too much time on the artistry of this problem. And you really do have to consider the artistry when it comes to drawing these projections in a way that is where it's easily evaluated by myself. Okay, so now if you look at all 6 of these structures, within reason, I have frozen the nuclear positions of carbon-4 and the hydrogens that are attached to carbon-3. Now what I want to do is rotate the front carbon substituents, that is the orange methyl group and the 2 orange hydrogens, in increments of 60 degrees. So what I want to do next is go ahead and label these angles. So this one will be 240 degrees. And this one will be 300 degrees. This one is 360 degrees, which is exactly the same as 0 degrees. And then, of course, 60 degrees and 120 degrees. So now these are already labeled. All right, now, as I rotate the methyl group 60 degrees clockwise, it will now eclipse with the blue hydrogen. And drawing these eclipses is a little bit on the tricky side. You can't completely superimpose them. But this works very well. And just so that there's a difference between the 2 hydrogens, I'm going to call this H1 and this one H2, so that we can track these throughout. Now I'm going to rotate another 60 degrees. And by this time, you should be getting the hang of the logic of making all these rotamers. So notice that this is a staggered arrangement, an eclipsed arrangement, a staggered arrangement, so they will alternate every other one. Of course, at 0 degrees, we're going to be staggered again. This is kind of difficult to show, but I want to show the two methyl groups are really on top of one another. As are the two hydrogens. Then of course we're going to have staggered again at 60 degrees. And finally we'll have eclipsed again. We have all 6 rotamers now present that represent the major dihedral angle equivalents of this molecule. Now, the sharp student's going to be asking the question, well, can't we do this at every angle? Sure, there are an infinite number, but I think it really makes sense to only look at the ones that are going to significantly differ in energy. And these 6 will represent the ones that are going to be most different in energy. We now, of course, want to rank all of these. So we're going to call the lowest energy number 1 because it is the lowest in energy. Highest in energy is number 6. Now, if we look at the other 2 staggareds, one's going to be number 2, one's going to be number 3. But since this is a symmetrical compound, the 60-degree rotamer and the 300-degree rotamer are of equivalent energy. So I'm going to call one of those 2, and I'm going to call the other one 2. There's no difference in the energy of these 2 rotamers. You have a gauche relationship between 2 methyl groups, and you have 2 gauche hydrogen methyls, and you have 1, 2, 3 hydrogen gauche. If we look at the 60 degree, there is a gauche between methyl-methyl. There are 2 methyl hydrogen gauche, and there are 1, 2, 3 hydrogen gauche. Similarly, the 240-degree rotamer and the 120-degree rotamer are equivalent in energy, so I'm going to call those 5 and 5. What this allows us to do now is to draw a relative scale potential energy diagram of these rotational or conformational isomers, which will be the last thing that you'll want to be able to do. And I'm going to want to label this starting at 0 degrees, then 60 degrees, 120, 180, 240, 300. And I'm going to go ahead and tag 360 on here. It is equivalent to 0, but it will show the complete cycle. And then, of course, I'm going to measure relative potential energy. So remember, 0 degrees and 360 degrees will be the highest in energy. 180 will be the lowest, 60 and 300 will be the second lowest, 120 and 240 will be the second highest. And now I can simply trace a curve. Assuming I can draw a curve. I did have issues in kindergarten. But I think you guys get the point. When you have drawn all of the rotamers and labeled them, and you draw the potential energy diagram in this form, that is all that I ask you be able to do. So, in class last week, I asked you to consider a molecule. I want to reframe this question, and I will probably also put this on a problem set. Let's consider the molecule 2,2,3,5 pentamethylhexane. Let's go ahead and draw that molecule. Not going to show any stereochemistry. There's the molecule. You need to draw all rotamers. In the Newman projection. You need to rank their energies. And you need to draw a potential energy diagram. That PED stands for potential energy diagram, not for performance enhancing drugs. PED. Those are the three things that I would ask you be able to do in the context of a take-home test question or in the context of an in-class exam question. It's a fairly comprehensive problem. You should expect it to take you about 15 minutes to complete this problem, but certainly this is a good one to start with so that you can assess your level of mastery on drawing these types of isomers. One last thing I'd like to discuss, and I previewed this in lab last week. We can look at rings in a slightly different way now. Cyclohexane is many times rendered as though it's planar. It is not planar. It has two major conformations. One is called the chair conformation. And I'm going to go ahead and label these carbons as C1, C2, C3, C4, C5, and C6. Also, another major conformation is the boat conformation. And you have the same numbering scheme. 1, 2, 3, 4, 5, and 6. we can use our Newman projections in the context of more complicated molecules. For example, we can look down the axes of the C2C3 and the C6C5 bonds simultaneously. Before I draw this for you, let's go back and look at the atomic dashboard and find a molecule and try to do this in 3 dimensions. Again, this is the Mac app I was discussing in class last week. And so what you do, it's a $15 app if you have an iMac at home or if you have a Mac laptop. You'll search the molecule. When you download it, it will pop up just as so. What I want to do is I want to rotate this molecule to convince you it is not a planar molecule. So I'm just going to rock this back, and then I'm going to rotate. And let's use a little bit of imagination. This is a chair. Here is the seat of the chair. Here is the head of the chair and the foot of the chair. This chair conformation is what I've actually drawn to the left. So let me go ahead and label these. This is the chair. This is the boat. The chair conformation is actually the lowest energy conformation that we can obtain given the constraints imposed upon it because it is a ring. Again, let's go back to the atomic dashboard, and I want us to look down the C2C3, and C6C5 bonds simultaneously. To do so, I'll need to rotate the molecule. Here is C5, here is C6, behind it is C5. Here is C2, behind it is C3. Here is C1, here is C4. Notice how one puckers up, one puckers down. That is the Newman projection. Also notice the arrangement of all the hydrogens are gauche. Also notice the CH2s are anti one to another. Beyond a shadow of a doubt, that is the lowest energy conformation that we can obtain. So now I'd like to draw that conformation for you. So first I'm going to draw the C6C5. And I'm actually going to fill them in. And then I'm going to draw the C2C3, also filling it in. Front carbons, I'm going to have those as green. Back carbons, we'll have those as blue. Guess I'm going Seattle Seahawks color scheme today, which doesn't make a lot of sense since I've never liked the Seahawks. I'm going to fill in the hydrogens. This does take more imagination than the first example with butane that I did for you earlier. So this is the Newman projection of the chair conformation of cyclohexane. Now, with the boat conformation, there will be some similarities. You're going to look down the C6, C5, and also the C2, C3. I'm going to do a mulligan on this. C6, C2. I'm going to render those in green. C3 and C5 I'm going to render in black. Now if you look down these bonds in your mind's eye, hopefully you can begin to see you're going to have an issue. These two CH2 groups are going to superimpose and be eclipsed. So my Newman conformation for the boat is going to have everything eclipsed. This introduces a lot of strain into the system, something we'll be talking about in class on Monday and Tuesday. So if you really consider the principles that we have discussed, you should easily see that the chair is the lowest energy conformation, while the boat is going to be the highest energy conformation. But this is a Newman projection rendering of these two states with rings. So I want you to take the theory and the practice that we have presented here and be able to attack your problem set. I am going to incorporate conformation with some mechanism, and so I'm not going to make this problem set due until the first day we come back after fall break. So if you're in my Monday, Wednesday class, then it will be due the Wednesday after fall break. If you're in my Tuesday, Thursday class, it will be due the Thursday after fall break. Expect that to be posted within the next day or so, preferably by tomorrow. But anyway, that concludes this particular Ozcast on Newman projections, and hopefully this helps you alleviate any of your concerns. If you still have questions or issues, make sure that you let me know.